So at the end of the last module, we began talking about the formal system, the underlying structural elements of probabilistic inferences that we want to be able to capture, to represent, to make explicit. And so we differentiated between simple events, events or descriptions of events that are made true or false by just one aspect of the world, and complex events, events that require more than one aspect or that can be made true in more than one way. And so probability theory is going to seek to compute or to prove the probability of those complex events from the probability of those simple events. And so in this way, it's a lot like our propositional logic, where we used our truth tables to determine the truth function or the truth value of more complex formulas based on the truth value of their simple constitutive statements together with their logical connectives. And this is exactly how probability theory will work as well, computing the probability of complex events by taking the probability of simple events and using our basic rules. So like other formal systems then, we can see or think of probability theory in terms of those three fundamental elements of a formal inference system. There's the formal system that renders the underlying structural elements and relationships explicit. There's the decision procedure that allows us to operate on those explicit representations to calculate solutions. And there's the translation heuristics that takes the world or our descriptions and translates them into the formal system and then translates the answers that it gives us back out into the world or our descriptions of it. And so like the formal systems for categorical logic and propositional logic, theorists crafted the formal system for probability theory to make it as simple to learn and to use as possible with as few compromises to its inferential power as possible. So capitalized letters are going to be the way that we symbolize simple events. And the probabilities of those simple events are going to get symbolized either as P with an A in parentheses, understood as the probability of event A, or as a numerical value that ranges from 0, which would be impossible, to 1, which would be necessary. And those numbers will be a function of the favorable outcomes, that is, the ways in which the event could be true, divided by the total number of possible outcomes. So for instance, the probability of rolling a 6 on a single roll of a fair die gets symbolized as the probability with the event letter in parentheses, so P parentheses S. And it has the approximate numerical value of 0.167, or favorable, one way of getting a 6, divided by the total number of possible, 6 different sides, so 1 divided by 6, or 0.167 approximately. So this is Edmund Halley. He wrote the first mortality tables relating death and age based upon work by John Grant. And he was, in addition to an astronomer, also a early statistician. So this brings us to how we actually get the numerical value for the probability of individual simple events. We're going to adopt a sort of pragmatic approach. We're going to use the interpretation of probability that is best suited for the given case that we're trying to work on. And we're going to use that interpretation as the basis for estimating the probabilities for our individual simple events. So recall that theorists have proposed 3 different interpretations, 3 ways of understanding probability or the likelihood of something going to happen. Classical theory defines probability as the number of favorable outcomes divided by the number of possible outcomes, so F divided by N. Now, importantly, it assumes the principle of indifference. Namely, it assumes that every possible outcome is equally likely. That is, there is no outcome that is more likely to happen than any other outcome. And so we get the ones that are favorable, we divide them by the total number possible, and that gives us our estimate. We can see how this is a nice way of estimating the likelihood of simple events for games of chance. That's the whole point of a game of chance. Every outcome in your game should be just as likely to happen as every other, otherwise your game is rigged. So it's a natural way of estimating likelihoods, adopting that principle of indifference, estimating likelihoods as f divided by n in classical probability theory. The classical theory looks best when it's applied to cases like games of chance, where there are finite logically possible alternatives and nothing about the rules favors one outcome over another. So, you go to the roulette table. There are, I don't know exactly how many different places the ball could land. Every one is just as likely as every other, and so it is a fair game. We can figure out how many possible outcomes there are. We can figure out the number of outcomes that will allow us to win, and we can divide that by assuming the principle of indifference, f divided by n. We still have 2 more interpretations to go, but I'm going to leave those to the next module because I don't want to go over 10 minutes for any given module.